2, 1. All right, answer for 1. D, good. So basically you just had to run some percents, and that's percent by mass. Okay, so looking at the atomic masses of those. Percent mass is always part over whole. So if we're looking at percent nitrogen and you see 2s and 2s and 2s, that means you're doubling those nitrogens because there are 2 subscripts. 2. B, okay, so you're looking for, again, percent mass, but we have hydrates here. So B has 7 waters. So 7, what's molar mass of water? Approximately 18. Now that does take some mental math, so hopefully you had a chance to attempt that with mental math, but I'm sure that was back in January or December. So then over the total mass would give us the percent water out of the total compound. 3. B, okay, so how do we get that? We looked for something. Common factor, right? So you look to see which of these, A, B, C, or A through E, which would go into each of these compound molar masses to get a full integer to get us to the point where we have like a full number of atoms of something, of X. 4. A, good. What did you have to set up? BDA table, so you had moles and moles. You had a limiting reagent of oxygen, and then you had to find yield of nitrogen monoxide and then go for percent yield. Or sorry, that is your theoretical yield. That is your yield. That would be the answer. So, 4 for 4? Can you say 3 for 4 or 2 for 4? Okay. All right, so I'm going to go back to free response in a minute. So 2, take a minute to look at those again because, you know, it's been a while. Take a minute to look over 2's. Okay, unit 2. Unit 2, multiple choice. Lots of words. Test 50%. I'm going to look back at your syllabus. Labs are worth 25 because we're supposed to spend at least 25% of the year in lab. And then homework is worth 15%. It might be 30% lab and 10% homework. I have to go back and check. Once I put that in the grading system, I'll go back. All right, come back to me. 3, 2, 1. Number 1, what did you guys say? C. What did you set up? Dilution equation, M1V1 equals M2V2, and then solve. 2. I heard A. Anything else? Question? Yeah?
So when can we use the dilution equation?
When you're diluting substances, that's it. Do not use it for titration. Yeah, so that's the problem. On honors chem, those teachers other than me, tell you can use M1V1 for 1-to-1 ratios with titrations. It works because technically you're diluting an acid and base or vice versa, but it's not conceptually correct. And AP Chem, the College Board does not accept it on the AP exam, so I stopped teaching that period. All right, so 2, you guys said what? A is actually the best answer. B is a common answer because you get 0.12 moles of the barium nitrate, but since the nitrate's the question, and barium nitrate forces twice the production of nitrate because of the 1-to-2 ratio within itself, it actually is half that. So that's why a misconception would be B, but the correct answer is A. So when you go through and you do find your moles of iron 3 nitrate, go to the moles of solid barium nitrate, and then go just to nitrate, it kind of shuffles them down with the ratio. So that would be 0.06. 3. C, good. So in this case, you had like 0.1 moles of the sodium chloride, which is producing 0.1 moles of chloride, and then 0.1 moles of calcium chloride, which produces how much chloride? Double, right? So 0.2, because there's there's 2 chlorides produced for every 1 mole of calcium chloride. So that's 0.1 plus 0.2 would give me 0.3. And so silver chloride precipitates in a 1-to-1 ratio with chloride, so that's why you need the same amount. 4. C, what did you have to set up? Probably a BDA. Maybe you could have done portions of that in your head, but who was your LR? Yeah, sulfuric acid, and then you had leftovers of barium chloride, and then you had to take that and divide it by the total liters of solution, which was 100 plus 100, so it'd be 0.2 liters, and then you get your new concentration. So that's been old, like that's like September old. Do we remember a little bit about our BDAs, stoic with like within solutions? As long as you're looking at the ratios, like if you had to find the chloride concentration, notice there's 2 chlorides, so it's going to be double. Like, that's the only thing people really mess up on, is forgetting the internal ratios. So I'm skipping 3 for a second because there's no true multiple choice. It's all balance, balance, balance. So let me go down to 4. Look at 4 for a second so you can remind yourself where you are. Hopefully you're taking a second to look back. It's been a while since you've done these, unless you did them all last night. All right, come back to me. 3, 2, 1. Number 1 answer. D is the best answer. What equation came to mind for this? Oh, you could have done ideal gas law. You also could have done molar mass equation, which is what? It's asking for molar mass, right? If I saw that question in gases was molar mass, and I knew that I had everything to plug it in, I would use the molar mass equation, which is what? Molar mass is equal to dirt. So D means what? Density, which is in grams per liter. Dirt RT over P. So that is something you can utilize, unless you want to go through, manipulating stuff a little bit more with the ideal gas. So that was D. Now, this one doesn't have any units, but I expect that there would likely be units. They did try to define everything in-house, though, except for Celsius, which had to go to Kelvin. 2. Say it louder. E as an elephant. Good. So what did you look at here? To answer these masses, right? So how many moles of hydrogen did this one have? How many moles of hydrogen is 0.5 grams? You can do that in your head. Come on. 0.25. So what you have to do mathematically in your head, and I guarantee you'll see something, maybe not like this exactly, but where you're taking moles and comparing numbers of moles of different things, and either finding who's got the highest molarity, who makes the most atoms, who has the fastest or who takes the most space. There's a lot of things you can compare with mole relationships. So 0.5 grams of hydrogen gas is equivalent to 0.25 moles. And then oxygen, we have 8 grams. So remember, these are all diatoms because they're in their natural state. So how many moles is this? 0.25. A lot of people make a mistake and do half 0.5 because of the molar mass of being 16 on the periodic table, but 32 is a diatomic. So, and then the equation that kind of applies, well, doesn't really matter. No, it does. 1/2 mv squared is equal to what? Velocity or kinetic energy. Average kinetic energy. Not average. Single particle. But that's something that's so difficult. All right, so 3. Ready? A, so you're looking at what again here? The masses, right? So who weighs the least? So it's going to be if using the fastest or slowest? Fastest, so is it left afterwards? Is it left over in high quantity? No, so it's going to escape the fastest and be the least. For this one, maybe it was challenging because we haven't talked about polarity extensively. But what are the two factors that makes the gas deviate from ideal gas behavior? So polarity and, okay, so if it's polar, it'll have more interactions. More interactions means that they kind of condense together and they don't collide as separate entities, so that deviates the pressure. And then size kind of does the same thing. Size can relate to interactions, but size also means it takes up more volume, so there's less play space, so then it's going to cause some sort of deviation of pressure again. So who's the best answer here? A, sulfur dioxide is actually polar, so it causes some deviations, but minimal expectation on polarity on your midterm because we have a whole unit on that in like March. Okay. Oh, sorry, second thought here. There are two conditions that would force gases to act more ideal. What are those conditions? So make them act ideal. Low temperature means they move really slow, so they have a chance to interact. So high temperatures means more ideal, and low pressure because they're spread out and they're not going to interact. So it's all about interactions. If you don't want interactions, spread them out, make them fast. And then deviations from ideal gas behavior would be what? What two conditions? Well, no, deviations from ideal gas conditions. Low temperatures and high pressures. These would be like characteristics of the substances. Okay, 5. Just double checking on it. Yeah, D. So what gas law did you kind of use here? Total pressure is equal to 2 partial pressures, so Dalton's law. And that would have to be like given to you, so if partial pressure wasn't given to you, then you're not going to do the math, it'll be just conceptual. Alrighty, 5. Oh, take a second to look over 5 again before we move on. All right, back to me. 3, 2, 1. Answer for 1. C. That is the best answer here. Entropy. Entropy is increasing because you're melting this, right? Yes, you're melting. So melting. Yeah, you should know anytime you're having state changes, the relative entropy changes and the relative enthalpy changes. So from solid to liquid to gas. Is this, of course, this is melting and vaporizing. Is this endo or exo in terms of the process that's required? So this has low kinetic energy because solids don't move very fast, they just kind of vibrate. Medium kinetic energy, and then high kinetic energy. So how would one get from a low kinetic energy to a medium kinetic energy? You gain energy. So hence you are endo. Most of you guys said exo. It's easy if you draw out and think about it for a second. You have to gain energy to go from solid to liquid because kinetic energy is a form of thermal energy. So this would be endo for the whole going from solid to gas, and then vice versa from gas to liquid to solid. The process of condensation and freezing are what kind of processes? Exo. Like they have to release energy to create a higher or lower kinetic energy, which would give us the different state of matter. These are exothermic physical processes, so we're not having chemical changes, they're all physical. So that's why you have like a delta H condensation. And so if we had a delta H condensation for gas to liquid, it's exothermic, so this would be a positive or negative value. Negative, And then if I had a delta H of vaporization, that would be a positive value. So some of those should be easily predicted from just your knowledge of kinetic energy. And then everything on the first example, this all does what with entropy? Increases, so that's a positive. And this all does decreasing entropy as we make it more ordered. All right, so 2. Because, and this is the part everybody likes to mess up, temperature is decreasing. It means it's getting colder. Rationalize that as the endo or exo. It's getting colder. It means you, the surroundings, are feeling something getting colder. Say again? It's endo. You have got to rationalize that. This is like a constant struggle through everybody's minds, but you are like technically giving energy to the system. It's absorbing energy. It's consuming it. It's used it. It's now cold. So that's endo. 3. Confidence, people. D. It is right, because you have essentially no volume changes. When you take 2 moles of gas to 2 moles of gas, and no volume changes means there's no work done. Work is the negative P delta V, which is what's incorporated into the total energy exchange. So if there's no volume change, there's no extra work done. So therefore, the energy is equal to H. All right, take a second, look back over 6. Queen is, oh, Queen, it's negative 5th. Negative 5th, negative 5th. 28, yeah. All right, come back to me. All right, so we've got 1, go. Loud and proud, come on. B as in boy, good. So you have, it tells you first order and second order, like you can't get that wrong. Do not use the balanced chemical equation for any coefficients to transport 2 exponents, unless it's a what? So you're saying it's an elementary step in a mechanism that's labeled the rate determining step. So it has to be an elementary step, period, for you to ever consider using coefficients as exponents. But yes, of course, to write the rate law, it has to be the rate determining step, the slow step. 2. E as in elephant, yes. So you had B tripling. B triple means B times 3 squared. What's 3 squared? 9, not 6. Math. 3. Say again? D, good. So you had, what did we have? Oh, rate data. I was like, what did we have? No information. So you had your rate table. Sorry if you could have found this on my website, but yeah, that does say negative 5th and negative 5th. So as you went from experiment 1 to 2, what happened to concentration? Doubled. What happened to rate? Quadrupled. So is it directly proportional? So like, is it this increases by 2, this increases by 2? No, so it's going to be second order, not first. And then going from there, you had to solve for K by plugging into the rate law. Little k, rate law constant K. 4. E as an elephant. This took some math, right? This took a little bit of time. How did you start this one? When you started off with T, which was given as what? Total of 72 minutes. It told you the half-life was 18 minutes. What did you guys do with half-life? Hold on, you had to solve for K. All right, so half-life, this is an important point because we haven't looked at kinetics in a hot second. So what is the half-life equation for first order? Because it tells you it's first order. What's the half-life equation? 0.692 over K. So if you're told half-life is 18 minutes? Yeah, half-life is 18 minutes. 0.692 over K. You have to solve for K first, because if not, you couldn't utilize the integrated rate law equation whatsoever. So you solve for K to get what? So 3.85 times 10 to the negative 2. What's the unit for K? Louder. I think we were allowed to use minutes all the way here. Yeah, this is establishing minutes, so I'm going to keep it in minutes. So this is per minute, also noted as minute to the negative first. So because your K comes over here, your minutes go over here, you're dividing by minutes. You guys, I'm not saying you suck at the units for kinetics, but you need to go back and look at your units for kinetics. So you have that, and then you have to plug it into the integrated rate law for first order, which would be what? This is on your reference table. There's no question, like, you know where to find that. What is the first order integrated rate law? ln of final concentrations equal to KT plus ln initial. You're given enough data to plug, and you need to solve for concentration final, right? So you probably solve for ln final, and then how did you get rid of ln? E, right? So 0.05 molar was perfect. That is not a mental math one. All right, so 5. D, this is basically which one's true, right? So you're trying to figure out, it's given that it's first order, which of these is going to be the correlation on the graph for first order. When it's versus time, though, it's always integrated, so you should know your integration. So first order is linear, ln versus time. Second order is linear with 1 over concentration versus time, and 0 order is linear with concentration versus time. Does that ring a bell? Okay, it's been a little while, so. All right, last bit. Look over 7 first. Like for a second, please. All right, back to me. We have like a minute left in class. Here we go. 1. E as in elephant. Good. 2. B as in boy. Good. 3. A as in apple. 4. D, you had to set up a what on 4? Ice, baby. Let's make sure you're good at ices, because it's been a while since we did an ice box. 5. Say again? B as in boy. Double check your math. 4 was D, dog. 5 is B, boy. Alright, so what I'm looking for tomorrow is that if you did not get a 100 on this holiday review, it's basically for effort. If you didn't even attempt something, I kind of circled it or put a question mark. So attempt it and then get back to me, and I will adjust your grade accordingly. Some of you guys just need to find the other half, because like you just didn't realize I was taking up the whole thing. But if you're happy with your 95, you keep that 95. But if you want something more, then give me the full thing. Study, but get some sleep. Okay? Do not lose your folder of knowledge. Yeah. I won't round anything because I've already added extra credit, and I give like the good people points, and that's a test grade. So if you're sitting like that, I've already done all that. Like I've already done study evidence, extra credit. That's why I do it throughout the year. Bye. Oh, good people points due tomorrow, please. Good people points due tomorrow. The latest Friday, because I can key in 100 real fast. But please give those to me. Okay.